On 10.3, we introduced something known as the polar coordinate system, which for most of you should not be entirely new. You should have seen this in your calculus, in your pre-calculus or in your trigonometry. But even if you didn't see it, it's not that hard of a concept. This is what we did on Friday last week, or 2 weeks ago now, thanks to spring break. And instead of measuring distances from axes in rectangular fashion, like using the rectangular coordinate system, we're measuring rotation of the ray that goes through a point and the distance from that point. And so we talked about how to graph in polar coordinates. We talked about how you can represent any polar coordinate in infinitely many different ways. Because all you got to do to get the same point is revolve yourself around the system. Now, if you need to go back and refresh your memory on this, I'm not going to reteach it. I've got the video posted online for you so you can go and rewatch the first half of this if you need to. So we also looked at, once we knew how to graph points, how to graph curves, functions of theta. R is some function of theta. So we're going to look at things like this today and do the calculus on them. But that means basically, and I talked about this last time, where it's kind of like you're sweeping out this drawing arm. So as this arm goes around in a circle, you've got a different distance at every given theta. Okay? So as we trace this out, we're going further and further out till we get to here at theta equals pi. And then as we come back in, we get close back to the center. And this curve, represented by r equals 1 minus cosine theta, is what we call a cardioid. You think of like cardiac, meaning heart, right? It's a heart-shaped curve laying on its side here. Turn your head sideways. It almost looks like it's Valentine's Day. Okay, we also mentioned at the very end that we can graph these things using Wolfram Alpha and Maple. In Wolfram Alpha, you just got to throw in the word polar and do a polar plot. In Maple, if you tell it coords equal polar, then it's going to graph this on a polar coordinate system instead of a rectangular coordinate system. I thought I'd show you real quick before I start the areas, or actually do some of these examples. In Maple, I'm going to release this. You don't necessarily have to go and do this at the same time, but you are more than welcome to. But we didn't do this in class last time. But I'm going to open up Maple here on the instructor's computer. You can watch it up there as soon as it loads. But what I'm going to do is I'm just going to plot this cardioid right there in Maple. Now, the advantage to Wolfram Alpha, we've said this over and over again, the reason why I do both Maple and Wolfram Alpha is that Wolfram Alpha is free, but it also has a lot of disadvantages. It's basically a one-time shot at a computer algebra system. What I mean by that is that you can only issue one command at a time, and Maple lets you do a lot more than that. It's a much more powerful, much more robust computing environment, because I can save variables, I can tweak one part of my formula and do it again, and then I could do a series of things, like I could graph a function, I could then take its derivative, and then I could graph its derivative, then I could find the length of the curve, all on one worksheet, instead of having to go back and just change my search on Wolfram Alpha. So that kind of development environment actually tends to be a little bit more robust and useful in many cases. But if only we're going to do one thing at a time, then Wolfram Alpha is just as good. I wanted to plot t, no, it was 1 minus, what was it, cosine of t? Yeah, 1 minus cosine t. That was the cardioid that we graphed up here. So, and again, I could use theta, but I'm going to use just cosine of t. From t equals 0 to 2 times pi. It's where you got to remember in Maple, pi is always capitalized to use that constant. But then I put a comma in here, and I say coords equal polar. So the plot command in Maple is just plot the function, comma, t equals the range. If I had just done that and left off the coords equal polar part of that, it would graph it as a rectangular curve, which a 1 minus a cosine is like taking the cosine wave, flipping it, and moving it up 1. Okay, so it would look like a wave that starts at the bottom and goes back up. Okay, looks like a cosine wave. That's if I did it on a rectangular coordinate system. In fact, I can verify that for you. If I take this out and just plot that, you're going to get the wave, and you're going to know you're doing something wrong. Why is it taking so long? Come on. There you go. It just starts at the bottom, goes up, and comes back down. Right? I graphed it in my head even faster than Maple could have done it, so it's frustrating. But you can obviously imagine that we could get much more complicated curves and see what happens with those. But if I change it to coords equal polar, now it's going to think of theta, or t in this case, as a radius, as an angle, and then the value of the function is how far you are away at that angle, and there you get the cardioid that you expect. Okay? And again, I think I've told you this before, but all the computers in this lab, as well as the computers in the library, have either Maple 2015 or at least Maple 18 installed on them. So if you wanted to use Maple to do your homework, it's just a matter of going to one of those locations to be able to plug it in to there. Okay, we did get started on this, but we ran out of time on Friday talking about how do we find the tangents. So at any given point on this curve, what's the slope of the tangent line? Okay, remember that the derivative is what gives you slopes, but you have to remember that slope in terms of a straight line means change in y over change in x, right? I cannot just come up here and say, take the derivative of r and let that be the slope on this graph, because it's not. What the derivative of r with respect to theta would be is how fast is the radius changing as theta changing. Slope on a graph like this, like if I was talking about this, don't draw this on yours, but I want to know what's the slope right there. What I'm actually thinking of is something in terms of the rectangular coordinate system, right? I want to know what this change in y over change in x is as the change in x goes to 0. Okay, so what we've got to do is, instead of taking just the derivative of f of theta, we need to come and think of it as a parametric curve and find dy dx. And that's what we derived here, and it turns out this is the formula that we get when we think of r as a function of theta and rewrite the curve, the polar curve, as a parametric curve. Okay? Why we start with parametric curves in chapter 10 is so that we can use some of the things that we derive for parametric curves for polar curves, because this right here, if we have r is some polar curve, function of theta, we can always write it as a parametric curve. Okay? So all polar curves can be parameterized. And that's going to be the key to how we do areas and how we do lengths in 10.4. But for now, if we want to find the slope of the tangent line, that's what we derived here. Is I took the derivative of y with respect to theta over the derivative of x with respect to theta. Right? Because that's the formula. Tangents for parametric curves. We just talked about that earlier. But now I've got to treat this as a product rule. A function of theta times a function of theta. So it's first times the derivative of the second, plus the second times the derivative of the first for dy d theta. And then on bottom it's first times the derivative of the second plus the second times the derivative of the first. So that's what we came up with. This, which can be rewritten this way. So this is the formula we need to know. So we're going to answer a couple of questions using the tangent for the cardioid. A couple blanks here we need to fill in. If r is 0, notice what dy dx looks like. Look at this in the red box that I've got right here. What happens if r is 0? Do you see it? This goes away, right? And this goes away. So you're left with dr d theta sine of theta over dr d theta cosine of theta, right? But these cancel. So what are you left with? Tangent of theta. As long as dr d theta is not 0. That's an important point to make because I can't cancel if I've got 0 over 0. Okay, a couple other questions. Another note, important note here. When you got a big fraction like this, you got a numerator over denominator. Okay? Horizontal tangents occur when the slope is 0, right? Horizontal means slope is 0. When is a fraction equal to 0? When the numerator is 0. So a horizontal tangent will occur when dr d theta sine of theta plus r cosine of theta is 0. So that's just a reminder. If you happen to be asked, when is this polar curve horizontal, you just have to set the numerator of the derivative equal to 0. When would a vertical tangent occur? When is it straight up and down? It's when it blows up on the bottom, right? Or I guess when the slope is undefined, which is when the bottom is 0, right? So dr d theta cosine of theta minus r sine of theta equals 0. Not when the bottom blows up, when the whole fraction blows up, because the bottom is going to 0. So if you set the denominator equal to 0, you'll find the vertical tangents. Unless they're both 0. Okay? If they're both 0, then it's not a vertical or a horizontal tangent. And there's actually one of those points on the cardioid. That should be slope here, not slop. All right, so let's do this cardioid. R is equal to 1 plus sine of theta. Now I left this on broadcasting because I want to go ahead and plot that real quick. I'm going to do 1 plus sine of t, for t goes from 0 to 2 times pi, just to see what it looks like. Chords equal polar. So it's an upside down heart in this case. Or another shape. Well, we're going to still call that cardioid. All right. So given this cardioid, we want to find the slope of the tangent when theta is equal to pi over 3. So how do you find the slope of the tangent of a polar curve? Use the equation. Okay? In our case, slope of tangent which we call dy dx, is dr d theta sine theta plus r cosine theta divided by dr d theta cosine of theta minus r sine theta. So we now got to plug everything in. What's dr d theta in our case? Derivative of this? Everybody see that's cosine? 0 plus cosine theta.
It's a rare occurrence.
So I'm going to plug in this right here into these places. Boom, boom. But I'm also going to plug in this up here, right here, and right here. Okay, so all together we have dy dx would be cosine of theta, sine of theta, plus 1 plus sine theta, cosine theta, all divided by dr d theta, which is, again, cosine of theta, times cosine of theta gives me cosine squared of theta, minus 1 plus sine theta cosine theta. Okay, so question 1 just asks us to plug in a single value of theta and find out what the result is. So I could do that here and then simplify. The second question asks me a few more questions about where it's horizontal, where it's vertical. So what I'm going to do is I'm going to simplify this further now to have this in a little bit simpler form, and maybe answering those questions will be a little bit easier instead of plugging in numbers and then simplifying, or then setting these equal to things and simplifying after that. So I'm going to distribute this here on top and here on bottom. Oh, that should have been a sign on bottom, right?
Yeah.
Sorry. Is that better? So distribute this, and on top I'll have cosine theta sine theta plus cosine theta plus cosine theta sine theta divided by cosine squared of theta minus sine theta minus sine squared theta. Okay. So actually on top I'm left with a 2 cosine theta sine theta plus cosine theta. On bottom, I'm going to put cosine squared and sine squared together, but they're subtracted. But in the back of my mind, I recognize a couple of things. This here and this here are both trig identities. So I pull out my reference page, unless I've left it in my differential equation. Look up on your reference page if we can simplify 2 cosine theta sine theta, and if we can simplify cosine squared minus sine squared.
Yeah, you can do both.
Okay, so what is 2 cosine theta sine theta equal to?
We do
Sine 2 theta. And then what's cosine squared theta minus sine squared theta?
cosine.
Cosine 2 theta?
Yeah.
So now what I've got is sine 2 theta plus cosine theta over cosine 2 theta minus sine theta. All right, so that makes part A at least a little bit easier, I think. dy dx at theta equals pi over 3 would give me sine of 2 pi over 3 plus cosine of pi over 3 divided by cosine 2 pi over 3 minus sine pi over 3. And you can look those up on your table if you need to. That's 1/2 plus square root of 3 over 2. This is a negative 1/2 minus square root of 3 over 2. Multiply through everything by 2, and I get 1 plus square root of 3 over negative 1 minus square root of 3. Actually, that's, if I factor out the minus 1 on bottom, the 1 plus square root of 3 cancels, and I get just negative 1. Okay, so at 11 o'clock, we're going to come back and we're going to finish up these notes. So we're at least ready to tackle the next section, which is areas. Okay? So bring back your 10.4 with you, and we'll work on those today at our 11 o'clock hour.